Hi, my name is Norm, an offering manager for ADG over Radar, EW, and Comment Systems. Welcome to IMS 2024. Here we're going to be talking about characterization, high-speed validation really, of an X-band transmit-receive module using our latest and greatest vector signal transceiver, vector network analyzer, and also the PXI platform as a whole. So how about you come on over here and we're going to look at what we're characterizing within the platform. Long story short is that we have an ADI beamformer chipset comprised of basically gain phase shifters and a transmit-receive module. Once again, transmit-receive module, it's basically going to be some switches and amplifiers in either direction. And then basically on here on the beamforming chipset, it's multiple channels of gain and phase adjustment. So we're going to want to be flexing all of those things in order to, of course, characterize our device. And so you can see what we have over here is we basically have our transmit-receive module connected over into our gain phase shifter system. And basically over these blue cables, we're coming over to our vector signal transceiver with our newest, latest and greatest single slot vector network analyzer. And so one of the ways that if you take a look at the whole system, what we'll be doing is not only using just the vector signal transceiver to look at the analog performance, the other thing that we're going to be doing is not only supplying the digital power and control, but we're also going to be doing the digital power and control, but the digital control over SPI to the lines on the chipset over here. Now that's relatively speaking low speed, it's about 5 megahertz worth of SPI signaling back and forth. But what we're going to be able to showcase is basically our ability to rapidly basically share control between analog and digital within the same platform to fully characterize not only the S parameters, but also the stability of gain and phase across multiple different things. And so one of the things that you'll see here is basically we're switching across all of the gain and phase stages within 5 gain segments and 32 phase segments. So nothing too great in terms of the overall performance, but this should give you a relatively good characteristic behavior. So this is our DC supply and current draw and our individual control words. And so what you can see in the upper plots up here are basically our S parameter analysis. Now our S parameter analysis, as you'd imagine, is basically looking across frequency, the amplitude and phase performance. We have S21 over to the left and S12 over to the right. Now we're in transmit mode, so it really only makes sense that we have data on the left. But if I go down to our control system down here, we're going to go ahead and move it over into the other mode, and you'll see that now we're going ahead and looking at the other channel. And we're going to go ahead and put it back into sweep mode, and now you can see as indeed we're changing the phase actively and stepping down basically the amplitude. So we're able to get the wideband performance. We're only looking from 5 to 20 gigahertz here. The VNA has the ability to go from 100 megahertz to 26.5 gigahertz. So quite a wide range. But one thing that you'll notice is that we have the vector signal transceiver in line with the VNA. Now right now the VNA is doing all the work. It's getting all of our S parameters, looking at our 2 ports, giving us basically those transmission coefficients. But if we go ahead and we pause our S parameter analysis, we're going to go ahead and do that and start to look at it in time. So let's go ahead and connect over there. And one of the things that you'll see after I kick it into the transmit mode is that you'll see very quickly once it goes ahead and sends all those digital command words. Now what we're doing is we're looking at basically all of the performance of all of those gains and phase stages at a single frequency. Now it's not all that different than what we were looking at on the VNA, but if you notice it took a few seconds to go ahead and characterize all of those gain phase stages. We're actually looking at the full ability to characterize this. Basically, if I were to go over here, within about 41 milliseconds, we're going ahead and sweeping across all of those gain and phase stages. Basically, maybe about 258 microseconds per individual segment. But you might compare those times, which is already blazing fast to characterize this, but we're only actually looking at about 160 microseconds worth of acquisition time. All of that other time is basically digital overhead, basically because of the data set. So it just kind of goes to show, and this isn't even as fast as we can go in analog, but it's a nominal pace where we can basically look at the stability on the graphs over to the right, basically looking at the power performance. We're less than 1/10 of a dB accuracy and stable over iteration after iteration over multiple, basically we're doing every 40 milliseconds we're getting updates here. And so the other thing that we can look at, so why would this kind of characterization matter? Well, somebody who's doing a radar system really expects that if I were to go ahead and control and command a digital control word to leave the magnitude at a fixed value, it shouldn't matter what phase I go to. But very clearly, as we adjust the phase, as illustrated here by the yellow, we can see very clearly a lot of variation in the magnitude of that beamforming system. And so we can even go through and kind of compare 2 points on the graph here, and very quickly you can tell that as I move between each one of these individual points on the polar plot, you can tell there's a bit of a droop in the individual amplitude as we go between each one of those discrete code words. And so that would basically lead to what's called squint in a radar beamforming system. Basically, it prevents a fine beam and it kind of spreads it out a little bit in terms of the fidelity of it. And so that's why being able to get this kind of information matters so much. But the differentiation of what we're looking at here is, whereas mostly people would use a VNA to do all that full characterization, but really the performance that you're looking at, you'd have to wait several seconds to get one amount of settings. Well, we have the ability to get all of those settings, 160 in total right now, once again, within about the 40 milliseconds. So one of the things that we can do, maybe you don't need 140 milliseconds worth of time, maybe that's less impressive for your application, but really one thing that I would postulate is what happens if you can get more information in the same time. So I'm going to go ahead and bump this up to say 24 discrete gain segments, and you can see we've got quite a few more radials that we're going to iterate across, and now you can see us doing that same type of analysis, but with a lot more insight. And the ability to look at the actual kind of characteristic behavior of each one of those segments, still underneath 200 milliseconds worth of time, can make a massive difference in terms of your ability to predict performance, the ability to model your system, the ability to actually see, hey, there's a very strange repetitive behavior or roll-off, kind of like what we're seeing up top there. So really, I'm going to go kick this back down to 5 for the moment. Actually, I'll just put it to 7. Let's see, put it there. And so really that big differentiation that we're showcasing here is not just the ability to get the insights like you would with any lab equipment. We have lab equipment here, but it's also the ability, once again, I'm going to go ahead and kick this to run over here. So really one of the things that we're going to have the ability to showcase here is that you're getting the insights that you need faster, but then also you're getting them fast. And the way that we're leveraging this is by doing proper automation. One of the things that people don't commonly do in basically test measurements when they have to do some degree of automation is you don't take advantage of the ability, even in PXI, to coordinate between instrumentations with hardware triggers and hardware timing. That's exactly what we have going on here. That's how we're able to get basically all of that measurement science within, once again, 225 microseconds for an even more dense pattern. Because what we're doing is we're telling the instruments, hey, I'm done sending my digital pattern, start your analysis, because the analyzer's already ready for it. But the other thing that's really unique with the NI system is we are going ahead and when we acquire the very last sample, not process the last result, but when we get the last sample, we're already indicating back to our digital system, start reprogramming your device under test. And so we end up in a test scenario of automation where we're basically sharing the time and overlapping digital control and the measurements, really giving you the ability to do what you would really want to do, but normally you wouldn't do because it would probably just take too long. Or if you're more in a manufacturing situation, the ability to just push more devices through the system. Also, still being able to get more insights because you still have the single connection of the VNA to give you the wideband analysis, basically 5 to 20 gigahertz in frequency domain, but also the VST giving you the generation and analysis capability to give you deep insights in terms of the beamformer performance that we're looking at here. So I hope that gives you a good insight of basically the NI system, which is not only doing digital and analog, heck, we didn't even mention the DC power and doing measurements like PAE, P1dB, noise figure, and TOI, but really hopefully that gives you a good insight as to the type of performance you can get from basically a mixed domain platform like NI has, where it's a natural fit to have automation, analog, RF, VNA, and digital all within the same package. Thank you very much.